And the talk will be divided into two parts. In the first part, will be giving some motivation and some literature about previous work in finite categories and in computational algebra. And in the second part, we'll be talking about simple semigroups in finite categories. So what we do is it is studying studying combinatorial algebra problem with the contribute of associative structures, because it's very normal when studying various types of groups and semigroups to try to solve the problem, how many of each type exist. And we have seen many combinatorial results in groups and monoids, and this will help us study finite categories. And since finite categories are associative structures, then this will deepen our understanding to the enumeration and classification problem in associative algebra in general. And counting associative structures has been a problem for years, and some tried to count by hand, and some used computer algebra systems to do to solve their problems. For example, in 2009, Dissler and Kelsey counted the number of monoids of order 8, 9, and 10. And then in 2012, they counted the number of semigroups of order 10. And in 2017, Alouche and Simpson counted the number of categories such that the number of morphisms between each two objects is 2. And we will be talking about that later also. But we will start with the definition of a category. So a category C consists of a set of objects that we will denote OP-C, and set of morphisms that link the object together that we will call it the hom C of XY or CXY, and a binary operation that we call composition of these morphisms, and we denote it by F dot G. And actually the correct multiplication should be G dot F and not F dot G, but in my work, I use the other direction because it's more practical. And this composition is associative, so it satisfies the associativity property. And there is an identity in each object. So for every object X, there's just one of X, such that for every morphism F and G, F times 1 equals F and 1 times G equals G. And for example, we have the category of groups. The objects are groups and morphisms are group homomorphisms, and category of topological spaces, the morphisms are continuous maps. Then I will define some structures. These are like 7 definitions. It's a lot, but if you can remember these definitions, because throughout the talk, we'll be mentioning all of them. So a finite category, and we're studying in particular finite categories. A finite category is a category whose set of objects and set of morphisms are finite. And a reduced category is just a category that does not have any 2 distinct isomorphic objects. So it means we don't have a morphism F and a morphism G such that their rounds are identities on both sides, of course, in order to have isomorphism. And a monoid is just a set with an associative binary operation and an identity element. And we can also see a monoid as a category with 1 object, which is very important because we need to see the objects of a category with the endomorphism set as monoids. And as an example of monoids, groups are monoids actually, but monoids are not groups. The difference is in groups, every morphism is invertible, but we have identity, we have associative binary operation, but the extra condition, which makes it stronger, is that every morphism is invertible, but in monoids, it's not always the case. And a semigroup is the weakest among them because it's just a set with an associative binary operation. So it doesn't even have a neutral element. A band is an idempotent semigroup. It means that every element is idempotent. A rectangular band is a band such that XYZ equals XZ. And finally, a semilattice is a commutative band. So it is an idempotent and commutative. Then we can associate finite categories or represent finite categories to as a square matrix, where the entries of the matrix are the number of morphisms between each two objects. For example, if we have this graph of a category, we have three objects, X, Y, and Z, and these are the morphisms between each two objects. Then the matrix associated to this category will be this. So between X and X, there are two morphisms. So here we have two between X and X. Between X and Y, we have one morphism. So we have one here. For example, between Z and X, we have three morphisms from Z to X. So Z to X, we have three in here. So this is the matrix associated to this category. And as a general definition, we say that a finite category is associated to a matrix M if the number of morphisms between each two objects in the category correspond or is equal to the corresponding entry in the matrix. And going from a category towards a matrix can be done in a unique way, but inversely we can obtain many categories for a single matrix, and this is what we'll be doing in here. And as a notation, we denote cat-red M as the set of finite reduced categories that are associated to M, because we're interested in studying only reduced categories. And we can also see the relation between finite categories and matrices as a function between them, such that this function is not injective, because, for example, if we take the matrix of size 1 and two elements inside, it means these are monoid because we have one object, and this monoid could have several categories. We could have several monoids of two elements, with two elements or three elements. And this function is also not surjective, and it means that we can have some matrices here that do not have pre-images. It means do not have categories. We take the example of this matrix 1, 2, 2, 1, and we suppose that this matrix admits a category. Then if it does, the graph of this matrix will be the following, and this is the graph of its category. We have, it's of size 2, then we have two objects, we call them X and Y. On the diagonals, we have 1 and 1, and it means that between, in the monoid parts, we only have one element here and one element here, and it's obligatory to be identities because there's always an identity. And between X and Y and X, there are two morphisms. We'll call them F1, F2, and G1, G2. And because of the associativity property, and because that F1 or F2 times G1, G2, it's always going to be equal to identity because the multiplication falls into X. And also G1, G2 by F1, F2, it's always going to fall into the identity of Y. Then because of these two conditions, we will obtain that G1 equals to G2. And this is a contradiction. So it means that this matrix doesn't admit a category at all. And this example actually shows the importance of associativity, because in other structures where we don't have associative property, we could obtain models to it. And the problem actually was that the other problem is that the diagonals were both 1, and we had only identities. Because if we had other than identities, it wouldn't have this, we wouldn't have obtained this problem. And because of this example, Berger and Leinster proved that if we have M square matrix and diagonals whose diagonals are at least 2, then we don't have 1 on the diagonals, then M is a matrix of a category. But then Alouche and Simpson wanted to know more that what happens if we have 1s on the diagonals. So they proved that if we have a matrix of size 2, 1, A, B, C, D, and if A, then this matrix admits a category, a reduced category, if and only if it satisfies one of these conditions. So if A is equal to 1, then the determinant of the matrix should be greater or equal to 1. And if D is equal to 1, it's the same condition. The determinant should be greater or equal than 1. Or both of the diagonals are not 1, so they're at least 2 by the previous theorem. But we conclude that the case where both of them are 1, it can't happen because of the example we showed before. And if we want to take this result to matrix of order 3, it's actually the same. So either all the diagonals are not 1, so strictly greater than 1, or if one of them is 1, let's say Z, then we take every submatrix of size 2 with Z here, and we do the determinant thing in each submatrix. And the same for n equals to 1 or r equals to 1. And for the general matrix, if I have a strictly positive matrix of order n, such that the first entry, so the first diagonal is 1, but all the other diagonals are not 1, then it admits a category if we take every submatrix of size 2 and we do the determinant thing, and it should work. But if we obtain, if we have another diagonal that is different from the first one and it is equal to 1, then there is no reduced category. And this is always because of the previous example. Then now we know what are the conditions on the matrix to obtain a category. And the question was, okay, if it admits a category, how many categories does it have? So I said that Allouche and Simpson counted the number of categories associated to the following matrices. So for size 1, there are 2 monoids, and for size 2, there are 1 category. For size 3, 5, and for n, there are only bounds. There is no exact number. And I'm going to try to, in the next slide, to explain why we have 2 monoids here and 1 category in here, so we can see the picture clearer, maybe. So for the monoid, for the matrix of size 1, and we have 2 elements. So it's 1 object. It's a category with 1 object, and there are 2 morphisms. We will call them 1 and 2. And we want to know the possible multiplication of these elements. So we want to know the table of multiplication of these elements. So we have 1, 2 by 1, 2, and 1 is identity. So it's always 1 times 2, it's going to be 2. But the question is 2 times 2. It has 2 possibilities. It is either 1 or it is either 2. And that's why you obtain 2 monoids. And in the first case here, it's clearly that this is the group Z2 because there's always going to be a group case among the cases. And we all know that there's only 1 group of order 2, which is Z2. So this is it. And the other monoid is not a group. Then if we treat the other matrix, it was 2, 2, 2, 2. So we have 2 objects that we call them XY. And we have 2 morphisms between each 2 objects. And we will call them 1, 2, 3, 4, 5, 6, and 7, 8, where 1 and 7 are the identities of the monoids, because there's always identities. And this is the table of multiplication of this category. So we are multiplying these elements together. First, I want to say that the zeros here are for the multiplication that is not defined. For example, we cannot multiply 1 times 5 because it doesn't satisfy the domain and codomain condition. It's not right. So 1 times anything is anything because it's identity. And actually, we know some parts, or we know we're going to obtain one category, so it's easy to figure out why. This is the first monoid part, so it is going to be one of these 2 monoids, and this is the second monoid part, and it's also going to be one of these 2 monoids. And why we chose the second one, it's 2 and 8, so we chose the second one only, because if we have 1 here, so we have a group, and we have it on both sides, and actually this will contradict with the condition that it is a reduced category. because at the end we will obtain invertible elements because we have groups on both sides. And actually, it's also not allowed even on one side because it's gonna cause a problem. And the main problem for that is that the number of morphisms here in X and in Y are the same. If it weren't the same, then we could have at least a group on one side. But we will not go into these details, but we will talk in the second part about groups, in the second part of the talk. And then why do we know also for sure this part of the multiplication? Because 3 times 5, it goes into X, so it's either 1 or 2. And it can't be 1, it can't be identity because it will also contradict with the reduced property. So it's equal to 2. So everything 3, 4 multiplied by 5 and 6, it's always going to be 2. So this part is 2. And the same for the second part, the second monoid is going to be 8. So it only remains to fill in these spots, and it's going to be easy to fill them out. We will obtain at the end one category up to isomorphism. And now what we did to improve this work, we wanted to push the counting problem further. And we start by counting the finite categories associated to matrices whose all coefficients are 3 instead of 2. And to do that, we write finite categories as certain expanded semigroups, and we use a program called maze4 to list all the models of the categories. And the input of maze4 are equations that are generated by a Python script. And these are equations of category, so of the category that we want to count. And we need to pay attention of the way of writing these equations because it may lead to keep the program running and running with no end. And actually, I will stop a little bit the sharing to share another screen to show you how the program actually works. So I will give an example, the example of 333. So I will share my screen. Okay, can you all see the screen, the Python script?
Yes.
Yes, okay. So this is the Python program, and in Python, all we do is we input the matrix that we want to count, which is going to correspond to the categories we are counting. So here we are counting 3, 3, 3, 3. We also can do it for size 1 and size 3 and everything. And it will generate equations of the category. And these equations we were going to put them in maze4. So here we have 2 objects, A and B. Between A, there are 3 morphisms, 1, 2, 3. Between A and B, 4, 5, 6. Between B and A, 7, 8, 9. And between B and B, 10, 11, 12. And the identities are 1 and 10. We need the associative property. We need the 0 element because of the multiplications that are not defined. So I say, which is everything is generated by the Python script. We say that 1 is identity. I just say this is the property of 1 and 10. And then I say this one here means that it cannot be equal to 1. It cannot be equal to identities because of the reduced property. So I say that the multiplication of morphisms are not identities. And this one here, it means or. So I give all the possibilities of the multiplication. So 2 times 2, it could be 1 or 2 or 3. It's the monoid part. So all of this is the monoid part until here 2 times 4, it is the monoid times the other set of morphisms. So it will be either 4 or 5 or 6. So we give maze4 all the possibilities, and at the end we give it all the non-defined compositions, which are equal to 0. And maze4 will do the count for us. We say that the domain is 13, the domain size, because we have 12 morphisms and the 0 element, so it makes it 13. And we start the program. And actually in the information, it shows us the seconds it takes to generate the models. And it shows us the models that the program found so far. And yeah, sometimes it takes a lot of time here, not so much, maybe 28 seconds or 30 seconds. And sometimes it's easy for Maze4 to count all the possibilities, but now after we want the models up to isomorphism, so it's hard for it to do it up to isomorphism. So I think it's done. Yeah, so these are all the possibilities. We have almost 36,000, around 36,000, but we want it up to isomorphism, so we isofilter. And we isofilter according to the identities 1 and 10, because we want to preserve the identities. So we run it again. And it will give us all the models up to isomorphism. So out of 36,000, we have 362 categories to the matrix 3333 up to isomorphism. These are all different categories. And here is the first monoid part. And here is the second monoid part. The zeros are for non-defined multiplication. This part is the monoid by the set of morphism from A to B, and etc. These are all different multiplications or different categories. I will return to the PDF file. Yeah, so sorry. So the theorem we obtain by Maze4 is that the number of categories associated to 3333 is 362 categories, which is a huge number of categories compared to the case where we had only 2222. It was one category. So it is much more than one. And actually, the reason is that for 2222, we had only one monoid to deal with on both sides, which was the monoid that wasn't a group. But here we have a monoid of size 3, and here is a monoid of size 3. And there are more possibilities than 1 or 2 as for monoids of size 2. So we will be interpreting the monoids of size 3 in order to understand what's happening to the category itself. So if I have a monoid of size 3, I will call the elements 1, 2, and 3. So 1, 2, and 3, and 1 is identity. And how many monoids of order 3 we can obtain? We can actually obtain, there are 7 monoids. We have 7 monoids. So each column is a monoid. And this is the table of multiplication of each monoid. I didn't put 1 because it's identity, but the others are like the first one, C1, for example, the first monoid, 2 times 2 is 1, 3 times 3 is 3, 2 times 3 is 3, and 3 times 2 is 3. This is the first model. And of course, we will have one of these monoids, it should be a group, which is C7, because we have 2 and 3 are inverses. So this is actually Z3. It is the only group of size 3. And all of the other monoids are not groups, but they have different algebraic structures from one another. And this is what we are going to do here. We're going to study their algebraic structures. So we will interpret each of the monoids. So C1 has a 0 element, which is 3, and an invertible element. And the 0 element, it means that it absorbs multiplication. It's actually the opposite of a neutral element. So when we multiply it by any other element, it gives you the 0. It gives you itself. And we can see in C1 that 3 is absorbing all the multiplication. So anything multiplied by 3 is 3. And 2 is invertible, it is equal to 1. And as for C2, it has a 0 and it is the element 2. And it's also obvious because 2 multiplied by anything is 2. So it's absorbing the multiplication. And C3 is a left rectangular band and C4 is a right rectangular band. And what does it mean? It means that it is a band first, so it's idempotent. 2 squared and 3 squared is equal to 2 and 3. And this is a left rectangular band because the multiplication is the left multiplication. So 2 times 3 is 2, 3 times 2 is 3. So it's taking the element on the left. And C4 is the opposite, it's taking the element on the right. So it's a 3 and 2, so 3 and 2 here. And C5 is of the form Z2 union 1. So it means that if we ignore the identity element 1, the set 2, 3 will form the group Z2. So if we just look at this part, we have 2 as a new identity, is the identity of Z2, and 3 is invertible. It's inverse is 3, so 3 squared is equal to 2. It's equal to the identity. And because 2 is identity, so 2 times 3 and 3 times 2 equals to 3. So C5 has a group, which is Z2 and plus the identity element. And C6 is semi-lattice, so it means it's a commutative band because 2, 3 is equal to 3, 2, and here it's the same. And C7 is the group Z3, as we said. And what do you want to do? We want to combine these monoids together as each 2 monoid together, for each monoid together and in one category. And we say that 2 monoids Ci and Cj are called connected if there exists a category where the monoids Ci and Cj are the endomorphism monoids of the 2 objects. So if there exists a category that connects them. And then if we view them as objects and each object is one of the monoids of endomorphisms listed before, then this graph of a category will be associated to the matrix 3, 3, 3, 3, because here we have 3 elements and 3 elements, and there are 3 morphisms between each 2 monoids. And what we want to do in maze 4 now is we want more information. So we have the equations of every monoid, and we want to say to maze 4, okay, I want to know the number of categories when I have this specific monoid here, let's say C1, and this specific monoid on the other side. So I specify the number of categories between each 2 monoids. And I get this table out. This is the output of maze 4. So between C1 and C1, we have exactly 10 categories. Between C1 and C2, we have 21. And it's the same as doing C2 and C1 because it's metric. And of course, the total of this number will be equal to 362 categories. But now we have exactly the exact number between each 2 monoids. And the most interesting part is that we have some zeros, and 0, it means that there is no category between C1 and C5, for example, or C2 and C5. And actually, C5 is a very interesting case because it's only connected to itself. It doesn't have any category with any other monoid except itself. And we will not actually discuss the reason of that now, but the main reason that it's only connected to itself is that because it contains a group Z2, we studied later the general case of C5 as if when we have a group of order n, not just 2, union a set of ordered identities, not just one identity, because C5 is just a group Z2 union one identity. But we classify the general case of C5 and we call it actually group-like monoids, if you want to know more about it, there's like an article about it on the archive called Classification of Group-like Categories. And it explains everything about these kinds of monoids in categories. And also in between C3 and C4, there isn't a category. And the main reason is because these are left rectangular band and this is a right rectangular band. And when we have rectangular bands, there are some restrictions on the matrix coefficients that are not satisfied in this case. But everything else, it seems that is a very, like the 362 is a very high number that could not be explained by hand, but actually we were able to explain most of the numbers here, and we also were able to explain why we have 123 between C6 and C6. So actually, it pretty much depends on the algebraic nature of the monoids. It's just not distributed randomly. And this is the conclusion of the first part, that the number of finite categories associated to a matrix is not distributed randomly between objects, and it actually depends on the algebraic nature of these monoids. But unfortunately, maze 4 is very limited by the size of the categories. So if I make this domain size bigger, it will crash and stop. But the more we know about the monoids and their algebraic structures, how do they affect the category itself, then we can add more equations and we can count more categories in this case. So this is all for the first part. If you have questions.
Okay, thank you, Najwa.
Thank you.